So we are curious about the source for a magnetic field in its simplest form. Just like we know that a point source, point charge particle, is the simplest source for an electric field. Think about a moving charge with a charge q at any instant of time moving with a velocity vector with this. So you wonder how this moving charge is creating a magnetic field around. Well, in order to find the exact expression for the magnetic field that this charge is creating, is first we have to choose a point to measure the magnetic field. Let's choose our point to be somewhere over here. And this is the point that we want to measure the magnetic field because of this charge moving in this direction at any instant of time. So this is the one instant of time that the charge is moving. Okay, we just freeze time, and we freeze time. We choose a point, and we want to measure the magnetic field at that point. If this is the location of the charge, and if this is the point that in question we want to measure the magnetic field, this must be the displacement vector from the location of the charge to the point in question we want to measure the magnetic field. So, you know, upon some many experiments, trials, empirically, this magnetic field is found to be equal to this expression. Mu0 divided by 4 pi, and mu0 is the one of the physical constants, just like epsilon 0. It is the magnetic permeability of free space, and 4 pi is just another constant. We know what the pi is, and this magnetic field is proportional to the charge in magnitude. If you double the charge, you double the magnetic field. And of course there comes the expression including the velocity and the displacement vector, and this cross product is to be divided by this distance or the displacement vectors cubed. Okay, so this is the expression, and it's very neat, but it is not a usual not a very common operation with the vectors of v and r. It's not a dot product or anything. Well, because we have the magnetic field as a vector, the result of operation of two vectors must be a vector, and the cross product is the only answer for that. So we just multiply the velocity vector of the particle at that instant with the displacement vector, and the result is going to be another vector. But we know that if v is in this direction and r is in this direction, we certainly know from the math, from calculus, that the cross product of these two vectors is going to be a vector which is perpendicular to the plane of v and r, and this is the plane of v and r. Okay, these two vectors are living a two-dimensional space, and it is exactly the plane of this board. Okay, because v is in this direction, and it is on this plane. R is on this plane, the same plane. So the result is going to be just the cross product of these two vectors on the same plane is going to be a vector which is perpendicular to this plane. But there are two directions for the result. Either your magnetic field is going to be out of this plane or into this plane. So what determines the direction? The direction is determined by your right-hand rule. Okay, it is this a right-hand rule that we can easily all the time we can use this rule, so to find the exact direction, the right direction. So in order to do that, what we do is we take our direction of the four fingers. This is your right hand, this is my right hand, you take the direction of 4 fingers in the direction of the first vector, because in the cross product there are 2 vectors. This is the first vector, this is the second vector. So you just give the direction of the 4 fingers in the direction of the first vector, which is the V over here. So this is exactly what you do. And your palm, this is your palm, okay, this is your palm. Your palm must face the second vector, okay, must face the second vector. Well, I can hold also this in this way, because in this orientation also my right hand, my 4 fingers shows the direction of the V, the velocity, but my palm is not facing R, it is facing this way. I must hold my 4 fingers so that it is facing R, you see. So next thing is that your thumb, which is into the page, is going to be direction for your magnetic field. Into page vectors are shown as cross with a circle around. Okay, a circle with cross sign shows that there's a vector over this point and it is into the page. Okay, so that's it. This is the direction and this is the magnitude. Well, of course, so this is the complete expression. Well, of course, if you are curious about the exact value of the magnitude of this B vector, you should know also the angle between these V and R. If this is theta, okay, if this angle is theta, the magnitude of B is going to be just mu0 divided by 4 pi multiplied by Q multiplied by V magnitude multiplied by R magnitude multiplied by sine of this angle, okay, sinus of this angle between V and R. And we have also R cube over here, and this is going to be your magnitude. So you see, this R and this R cube just simplifies. We would have just R square in the denominator, okay. So this shows also that just like electric field, the magnetic strength of the magnetic field drops by distance squared. Remember, this is for electric field, Q over R square. So the electric field drops by the distance squared, just like this one. Also the magnetic field drops by 1 over R square. Although you see R cube over here, since we have R in the denominator, these will cancel out and we will have it 1 over R square, 1 over distance square dependence for the magnetic field. Okay, so let's now do an example that in order to just use this formula, let's think about the moving charge particle, which is moving in this direction, in the direction of positive x, and it is moving parallel to the x direction with let's say the velocity magnitude of 3 times 10 to 6 meter per second, okay, with a charge of 4.5 nanocoulomb. And the question is, when the charge is at this location, the location is with respect to this origin, also given as a position vector, which is minus 4i plus 3j, okay. So it is at minus 4 meters, this point, and it is at plus 3 meters in the y direction. So when right at this location, this charge, what is the magnetic field created at the origin? Okay, so let's also draw this displacement vector from the charge location to the origin. So this is going to be your R vector, displacement vector, but you have to be careful over here. This R vector and this location, let's give it a different name for this one, the location of the particle with respect to this coordinate system, and this is the displacement vector from the location of the particle to the origin, they are different. I hope you understand the difference. Well, the location, the position of the object with respect to this origin is measured is a vector from this point towards the particle. But the displacement vector from the location of the particle to the point in question is this vector. So that means this r vector and this r prime vector are just inverse of each other. I mean, one of them is minus of the other. So the displacement vector r is going to be just minus r prime. So negative of this, your displacement vector is going to be 4 plus 4i minus 3j. Okay. So this point is important because, you know, the magnetic field expression is given in terms of this displacement vector, not the displacement from the point to the location, but from the location of the particle to the point. Okay, so once we fix this, we can just use this expression for B, and moreover, let's also write down V, velocity vector, in terms of the unit vectors I and j. So this is, we said that the particle is moving in the direction of x. It is magnitude with 3 times 10 to 6 meter per second. It is just 3 times 10 to 6 I, because it has only one component, which is in the direction of x. There is no any y component. That's it. This is your wave vector. So once we know these vectors, the rest is just doing this calculation. And Q and V, let's put the numbers over here. Okay, so by the way, this mu0 that I forgot to give you the magnitude, it is nothing but 4 pi multiplied by 10 to minus 7 and Newton per ampere square. Its unit is Newton per ampere square in SI unit system, of course. So let's put the numbers over here. Okay. Oops. And Q is just 4.5 times 10 to minus 9 because it's nanocoulomb. And V is 3 times 10 to 6 I, and cross product with 4I minus 3J. And these are in units of meter. This is in units of meter per second. And we want this to be divided by the cube of this vector. That means R is just the length square. Sorry, R is just the length of this vector, which is nothing but by using Pythagorean theorem it is going to be 5 meters, and it is going to be divided by 5 cube. Okay. So the next thing is just the I cross 4I minus 3J. I cross I is 0, and I cross J is K. We know that I cross J is K. So if you all do this, you get as a result, if you plug all these numbers into your calculator, you're going to find as minus 3.24 times 10 to minus 14 Tesla, and it is, since it is a vector with a unit vector k, and k is the unit vector in the direction of z. Well, if you look at over here, what is this direction? Is it going in or is it going out? Well, k is out, right? If your coordinate system like x is over here, y is in this direction, your k is going to be out of the page. And since we have minus k, the B vector is going to be into the page. Okay, it is going to be into the page, so that means B is, at this point, it is into the page. You just draw a circle with a cross inside. Okay, that's it. This is how you calculate the magnetic field for a point charge if you know the charge velocity, the charge magnitude, and the distance of the point to the charge.